Hello, curious minds. Scientists say the universe is 13.8 billion years old, but have you ever wondered how we know that? It's not like the universe came with a birth certificate, right? Today, we're breaking down the science behind how we cracked the biggest age mystery in the cosmos. Alright, let's talk about one of the biggest pieces of evidence for the universe's age, something you can't see with your eyes but is literally everywhere around you. The cosmic microwave background radiation, or CMB. Back in 1964, two scientists, Arno Penzias and Robert Wilson, were working on a radio antenna when they picked up a strange, persistent noise. No matter where they pointed their antenna, the noise was still there. At first they thought it was interference, maybe from the city or even pigeons nesting in their equipment. But what they actually discovered was the afterglow of the Big Bang itself. The CMB is faint microwave radiation that fills the entire universe, a leftover heat signature from when the universe was just 380,000 years old. Before that, the universe was too hot and dense for light to travel freely. But once things cooled down, light was finally able to escape, leaving behind this faint glow, like an ancient cosmic fingerprint. So how does this tell us the age of the universe? Scientists have studied tiny variations in the CMB's temperature, mapping out how matter was distributed in the early universe. These fluctuations act like a cosmic blueprint, telling us about the density, composition, and expansion rate of the universe. And here's the key: if scientists can estimate how far the CMB's light has traveled to reach Earth, they can calculate the universe's age. By combining this with our understanding of cosmic expansion, we can essentially rewind the universe to its very beginning. And when we do that, all the evidence points to the same answer, about 13.8 billion years. And here's something crazy. If you ever see static on an old TV, or hear white noise on a radio, a tiny fraction of that signal could come from the cosmic microwave background, so you're literally listening to the afterglow of the Big Bang. But to fully understand how the universe has evolved, we need to look at its ongoing expansion, something we can measure using Redshift. When we observe galaxies moving away from us, their light stretches out, shifting to the red end of the spectrum. This redshift is evidence of the universe's expansion, and it's key to understanding how galaxies are moving through space. This shift toward red light will lead us right into our next chapter. So, let's talk about another crucial piece of the puzzle: the expansion of the universe, and how we can use it to estimate the universe's age. And the key to understanding this expansion lies in a groundbreaking discovery by a scientist named Edwin Hubble. In the 1920s, Hubble made a shocking observation. He noticed that distant galaxies were moving away from us, and the farther a galaxy was, the faster it was receding. In other words, galaxies were receding from us in all directions, like raisins in a loaf of bread that's rising in the oven. This is known as the expansion of the universe, and it's still happening today. This led to what we now call Hubble's law, which states that the farther a galaxy is from us, the faster it's moving away. The relationship between distance and speed is linear, meaning if a galaxy is twice as far away, it's moving twice as fast. This observation is key because it tells us the universe has been expanding since its very beginning. Now, why does this matter for calculating the age of the universe? Well, if we know that galaxies are receding from each other, we can essentially rewind the expansion and figure out when everything was together, at the very beginning. By measuring how fast galaxies are moving away from us and knowing how long they've been expanding, scientists can estimate the time it took for the universe to stretch from that initial Big Bang moment to where it is now. The key to this calculation is what's called the Hubble constant, the rate at which the universe is expanding. By measuring this rate and plugging it into our models of cosmic expansion, we can determine how long the universe has been stretching. And that time, well, it tells us that the universe is approximately 13.8 billion years old. Again. Another fascinating way scientists figure out the universe's age is by studying star clusters and some of the oldest objects in the universe. One of the most exciting discoveries is that some of the oldest globular clusters contain stars that are estimated to be around 13 billion years old, nearly as old as the universe itself. But it's not just star clusters that help us understand the universe's age. Some of the oldest stars we've found are white dwarfs. These act as fossils, telling us when certain types of stars formed. For example, a white dwarf discovered in the star cluster NGC 6397 is estimated to be around 13 billion years old, providing more evidence that the universe is, at minimum, that old. But how do scientists actually measure the age of a star? Well, it's not just about how far away it is. One method is by looking at a star's mass, temperature, and brightness. Less massive stars burn cooler and last longer, while more massive stars burn hotter and faster, so they age quickly and burn out earlier. However, there's another clever method scientists use called gyrochronology. Over time, stars slow down their spinning, similar to how a spinning wheel slows when it encounters friction. This happens because of the loss of angular momentum as they age. By comparing the spin speeds of stars of different ages, astronomers have been able to develop mathematical relationships to estimate the ages of stars. Pretty cool, right? By studying these ancient stars, scientists can even estimate when the very first stars formed, helping us track the evolution of the universe after the Big Bang. Up next, let's get help from modern technology: computer simulations. These powerful tools allow us to peer back in time and recreate the universe's earliest moments, helping us understand how it all began and how we can pinpoint its age. These simulations use complex mathematical models based on physics, everything from the behavior of matter and energy to how gravity affects galaxies. By inputting known data, like the distribution of matter and the laws of physics, the simulations allow scientists to see how the universe might have evolved over billions of years. But simulations alone aren't enough. This is where cross-checking comes in. Scientists don't just trust the models blindly. They compare the results of these simulations with actual observations from telescopes, space probes, and other instruments. For example, they check if the simulated distribution of galaxies matches the cosmic microwave background, or if the predicted rate of expansion aligns with what we see in the sky. If the models line up with reality, then scientists gain more confidence in their conclusions about the universe's age. These cross-checks are crucial because they allow scientists to refine their models, making them more accurate over time. By combining computer simulations with observations, scientists have built an incredibly detailed picture of the universe's history. Ultimately, it all adds up to the conclusion that the universe is about 13.8 billion years old. And that's how we know the universe is 13.8 billion years old. From cosmic radiation to expanding galaxies, the clues are all around us, if we know where to look. But here's something to think about. If we could measure time before the Big Bang, what do you think we'd find? A past universe, a loop, or something even weirder? Let us know your theories in the comments. And if you love exploring the mysteries of space, don't forget to like, subscribe, and hit the bell so you never miss a new adventure. Thanks for watching. Until next time, keep looking up.